All right, this is the beginning of Unit 3. We're going to talk about energy a lot. I love energy. Energy's very interesting. I hope you'll like energy. So let's talk about it a little bit. We're going to spend some time just considering the bigger picture, and then we'll think about how to apply this on the subatomic or the microscopic point of view. All right, so first let's think about it. Instead of thermochemistry, let's just consider energy for just a minute. Okay, energy can be transferred. All right, what kind of energy do we have, and what's normal to use? So we have, hey, hydroelectric power plants, for example. Water, electricity. Well, water will generate the electricity up in your house. We could collect solar power, and certainly we're not very good at it. We're pretty inefficient, but plants are very good at collecting solar power. Maybe we can collect wind power and do something with that. We can even burn oil for absolutely no reason except the idea of burning it. That's transferring energy. All right, so let's think for a little second. Let's consider something we're more familiar with, or all familiar with, and that's water. Okay, we're just going to think about physical things that happen to it. So here we are. Let's call this the ocean. Okay, and our great little sun comes out, transfers energy to the water by solar energy. It heats up. Okay, so the water's going to heat up, and it's going to evaporate. Okay, hopefully it's not going to boil. That'd be bad, but evaporates into H2O gas. Hangs out in the atmosphere for a little while, and maybe a big storm comes along. Okay, get a new thing. Liquid. Here's H2O liquid. Again, we have a transfer of energy. Okay, and that transfer of energy is from the water in the gaseous form into energy outside of that, and we end up getting, let's see, energy lost, and our water becomes liquid again. Okay. So those are kind of energies that we're going to think about. All kinds, actually, but just think in big terms. All right, so we're going to be studying thermochemistry. Thermochemistry is a special branch of something called thermodynamics, and thermodynamics is dealing with chemical and physical heat and energy exchanges. And the main idea of thermochemistry is energy is transferred from one thing to another, and what happens is either work and heat or just heat. Okay, work and heat or just heat. Okay, any amount of work that's done is going to involve some inefficiency, and there's going to be some heat lost. Okay, or you could do no work, like just burn some propane and do nothing with it, just burn it, and all you get is heat. Okay, we're going to have to think carefully about something called the system and the surroundings. Okay, but we'll come back to that. Now, every system, everything has some internal energy, which is either called E or U. Okay, E or U. Sometimes I'll write it IE. So what I want you to do, stop everything you're doing right this second. Don't do anything. Just sit here and listen to me. Don't bat your eyes or anything. Consider for just 10 seconds, maybe 5. How much energy do you have? Do you have a state of energy? And the answer is, even if you're not doing anything at all, right, allegedly, anything at all, then you you still have some internal energy. Some amount of you is just at a specific energy state. Okay? And so I want you to think first about you, and then we'll take it down into smaller and smaller components. All right. Now, let's go back to our physical states of matter for just a minute. We have looked at solids, you know, they hold in a specific space. Liquids, they can take up more space. And gases will take up all the space. All right. Each of these physical states of matter has a specific amount of energy, no matter what it is. Now, our kinetic energies in the solid is just the vibration. There's a vibration between the atoms, between the molecules. The liquids can vibrate. They can vibrate. They can turn in space, so they can rotate. And they also will move past each other, so they can translate. Okay, they're kind of confined to a specific amount of space, but they can do all that. Gases do all these things, but with more energy. So, in terms of energy, this would have low kinetic energy. Oops, that's a K. This one would have high kinetic energy, just because of their physical states and how they act in those specific physical states. All right, so every system, no matter what, has some amount of kinetic energy. Okay, kinetic energy is the result of motion, and we just looked at vibration, rotation, and translation. There are other kinds of kinetic energies. For example, one of the things we'll be looking at throughout this semester is electrons. Electrons are the basis of chemical reactions, and in addition to these bigger atoms and molecules or whatever, there's also the motion of the electron, of specific electrons associated with specific things. Okay, so that also is a form of kinetic energy. All right, what about potential energy? Okay, so I think most people get kinetic energy pretty quickly. Potential energy, however, is an energy due to something we call position. Okay, and the classic example for a position is some kind of physical position. For example, we could have a rock. It's rolling down the hill. It has a specific amount of potential energy up here. And that potential energy might be the mass times the gravity times the height, okay, which, by the way, is kilograms per meter times meter squared per second squared. Okay, we'll see that later. So the rock has some potential energy, and somehow it begins to slide, and it slides and it slides and it slides, and it's sliding, 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 and then maybe it'll come to rest right here. Okay, and it has a new potential energy. Or maybe it has it's gathered a lot of kinetic energy as it's moving down, and it'll end up down here. Okay, the potential energy is changed to kinetic energy as the rock moves down the hill. Okay, and then once you get to wherever the rock is stable, here or here, you now have a new potential energy position. Okay, so that's like the classical physical potential energy. There's also potential energy related to gravitation and electrostatic energy and so forth. All those are types of potential energy. But in chemical energy, I want us to focus on where the potential energy is held. Okay, so the bonds and the intermolecular forces, both of which we'll spend more time thinking about later, are the things that hold chemical, or that hold the potential energy in a chemical. Now, I want to boil this down even more. I'm going to erase my classic physical example for a minute. And let's look at what do we mean by energy due to position in chemical reactions. Okay, first of all, basically, both of these are the attractive and the repulsive forces between the nuclei and electron. We can consider this one nucleus or two nucleuses or more. Just, I'm going to stick to one for just this very second. So let's assume we've got a nucleus. It's got some positive charge. It's got some neutrons. Okay. There's an electron out here somewhere, and there's an electron here somewhere. These repulse each other. They're the same charge. They repulse, right? But there's also an attraction from the electron to the nucleus on both of those, and those are attractions. Somewhere at just the right distance and just the right energy, the electron and the electrons and the protons form an element or a molecule or whatever we're talking about because of those electron attractive and repulsive forces. So I want to talk a bit for just a second about some of these forces. Okay, so forces. Oops. Forces. Can't spell. I once could spell before I started doing chemistry. Ruined my mind. So in the forces, there's electrons held to the nucleus. Okay, some positive charge and negative charge are being attracted to each other. And these electrons can be lost or they can gain, or the atom, either you can lose some electrons or the atom can gain some electrons, and these are what we call ions. Okay, we'll also have covalent molecules. Covalent, remember, they share their electrons, so lost or gained or shared. Okay, so those are forces between the electrons and the nucleus. Now, I just want to point out, well, this really is kind of tangential. We also have something called the strong force. Have you ever stopped to consider what holds the nucleus with all those positive charges together? Normally, we'd expect that nucleus to explode out into, space because there's too much positive charge built up in there. So it's actually the neutrons that provide this strong force and hold the nucleus together. All right, so these bonds and these intermolecular forces, whatever the state of the thing is, have a specific amount of heat, of energy. And those things are held in potential energy in terms of where the electrons are and how it's held to the nucleus, how they interact with each other, and then, of course, there's this strong force that holds your nucleus together. Okay, and on top of that, there's also some of this kinetic energy of some sort going on in every molecule or every atom that we're considering. All right, so here you are back to resting, being as still as you possibly can, no matter what. Okay, in that case, you have some specific amount of energy that internal energy. Okay, you have some potential energy and some kinetic energy, but that can't be very well measured, right? I mean, how do we figure out what your energy state is very well? We can, instead of doing what that energy state is right this minute, instead lift your hand up in the air with your pencil, and now you've had a change in energy, okay? Instead, we can figure out not the actual energy usually, but the change in energy, the difference from being real still to lifting your hand up, okay, or whatever. And in these cases, there's a formula here. You take the final energy position minus the initial energy position. Well, that doesn't really help very much because we still don't know what those states are or where those conditions are. Okay, so instead, as chemists, we take this heat and work concept. Q is heat, and work, shockingly, is W. Okay, put those together, we can measure that stuff, and then we can figure out what this change in energy was. Okay, what that change is. That's something we can figure out and measure. We may not be able to figure out where we started or where we end specifically, but we can figure out the difference. All right. Now, in chemistry, although this isn't how the human body works, we do a lot of work with the energy we intake. In chemistry, though, because either the change in energy is heat or work, or some combination of those, we focus and we work our very best to have only heat as the change in energy. And that's because we can measure heat easier than we can measure work. Okay, there's some work, obviously physics does that all the time, but we're going to just consider how much heat we get out. Okay, so we're going to be thinking about Q. We're going to be thinking about a system. Again, we'll come back to that, okay? But our main focus is on heat, Q. Q is what we want to know. Oh, yes, I had some great examples I wanted to share with you. All right. So let's assume for a minute that you just ate breakfast or dinner or whatever, okay? And so how do we figure out how much that stuff you ate gives you in potential energy? Okay, well, we use calorimetry. There's a couple of different forms, but one we'll focus on mostly to measure Q. Now remember, our purpose in chemistry is to take out all work and measure everything as heat. Okay, so we might take your breakfast sandwich and combust it, because it's got carbon in it, combust it into its components and figure out how much heat there was with this reaction. And we'll try to do as little or very little work, or no work preferably, if we can. Let me see. What else? So you take the full thing and get as much heat as you can. What if you have some work? Okay, what if you can't eliminate all work? All right, well, sometimes you can find that the pressure, delta V, is essentially very, very small. I want to make an example. For example, let's assume you have something like a 75-watt light bulb. Just a regular old-fashioned light bulb. I have one in my closet. I actually meant to bring it with me. It hasn't got a cover on it. So I reach up and I pull the little string, and my light comes on. And so I look for whatever I need, and then I reach up and turn it off. Well, when I first moved into that house, I spent a lot of time burning my fingers, because in the light bulb, a about 5% produces light. Very inefficient. And the other 95% is given off as heat. Okay, so in comparison, most of the work that was done in that light bulb is very small compared to the amount of heat. Which always reminds me of Edison. Gosh, I'm doing well today. Edison, a fantastic scientist who invented a useful light bulb. Edison always said, you know, genius is 1% inspiration and 99% perspiration, or something like that. So when Edison made this light bulb, he tried like roughly 2,000 different filaments before he could get a light bulb that actually produced light for more than, you know, a few minutes. So just because it's not very efficient doesn't mean it wasn't a really great find. It certainly changed our society. All right, so the law of energy conservation. So how are we going to use this? Well, if we know that work and heat are always conserved as energy, okay? Doesn't matter how we come about getting that decision, okay? We've conserved energy. The energy of the universe is going to be equal to whatever the change in the energy of the system, which in this case is you and me right now, plus the energy that we either take in or give off from the surroundings. Those both have to be equal to 0. Okay, add them together, there's no change in the universe. So for our system, in this case right this second, we're thinking about us. For our system, in order to lift our arm, we have to use up some energy, okay? And that energy has to go out to the surroundings. And I want you to notice that because these are equal to 0, our system and our surroundings have the exact same amount of energy change, but with opposite signs. Okay, that'll come back several times. All right, so here we are finally to the systems and surrounding business. Okay, now this is absolutely critical. It should be your first, thinking when you begin working on these. What is your system and what is your surroundings? You can define those, okay, as something, okay? So for our purposes, we're going to use the chemical or the physical reaction as the system. And then in theory, everything else outside of that chemical and physical reaction is called the surroundings. But, you know, we can't measure everything else. We have to have something that can actually be measured in some manner because this is chemistry and we measure everything. And so we have to define our surroundings somehow. A lot of times we're going to see that our surrounding is the water from the reaction where the reaction is occurring. Sometimes we'll use the calorimeter, okay, as part of the surroundings. Sometimes we won't. Maybe the room that I'm in right this second is my surroundings. I jump up, and then, you know, the energy I just released is released into the room. So I might want to measure my pressure and volume and those kind of things. It's probably too big of a system, but I mean, it could be defined that way. Too big of a surrounding, I'm sorry. Some other terms that you really must get into your head and really must understand. Once you have your system and your surroundings, you need to decide which way the energy, right now, we'll think about enthalpy in a minute. For just this second, want to know which way is the energy flowing. Okay? Exothermic reactions release heat from the system. So even though I'm just standing here, try not to move one little bit. Okay? I'm still releasing heat from the bodily processes that are going on in me. Okay? and that's exothermic. Exothermic is indicated with a delta H, a negative sign, negative, 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 meaning it's going out of me and out somewhere else into the surroundings. And we're going to be spending some time with something called enthalpy. Enthalpy is an approximation of the heat. The other thing that you need to understand is endothermic reactions. So in that case, you absorb energy, or the system absorbs energy from the surroundings, okay? And in this case, that's going to be a positive number. So any chemical reaction that we look at, okay, so here's ammonia and oxygen being combusted into nitrogen monoxide and some water. Okay, any chemical reaction is going to have some amount of heat and some amount of work. Okay, we'll try to keep it just heat, okay, as these bonds rearrange to form the products. Okay, likewise, ammonia, which is decomposed into hydrogen and nitrogen, ends up needing energy for this reaction to occur. Okay, so you need to keep straight what's positive, what's negative, what's exothermic, and what's endothermic. Those are critical, and they're always from the system's point of view. All right, so we only care about what the system is, okay? When we define the system, as I said, that ought to be practically your first thinking when you're thinking about these things. All right, now I also want to mention for just a minute the difference between heat and temperature. Okay, so heat is called thermal energy. Thermal energy. That's an energy, okay, energy. It's not the same thing as temperature. It has some substance. It's going to have some potential energy and some kinetic energy just because it exists. And all of the internal energy of the system is going to add up to give you the energy of the system. This is dependent on the amount and the temperature. Okay, so notice that if the energy is dependent in part on the temperature, then temperature must be something separate, which it is. Temperature is a measurement. It tells us something about the environment. Okay, so it's not, temperature and heat are not the same thing. Heat is energy, temperature is a data point. All right, now we're going to translate our Q, okay, our Q into something called enthalpy. Delta H is the change in enthalpy. Okay, and things that affect Q and the delta H are the amount of the material. All right, so if you have 10 grams that releases 200 kilojoules, which by the way you would say minus 200 kilojoules because it's being released, then if you double that amount, then you would expect this to be minus 400 kilojoules. Okay, so it depends on the amount. It matters whether you have a gram or a ton. Okay. The direction of the reaction also matters. Okay. Although our bodies are efficient and they use up lots of work, in theory we can go to our calorimeter and we can figure out how much some amount of food is in terms of delta H or our Q. If we eat that food, then we would expect to see, maybe not all of it, but some amount of heat being brought into our system. And also, once we release it, we would expect to see the same amount released into the surroundings. So the direction is important. And again, notice that that has a sign. It matters whether it's going in or coming out of the system. And maybe it's hard to figure out one reaction, okay, because something is harder to determine. Maybe we have a difficult time figuring out what amount of energy is involved in a reaction from A to C. But if we know a reaction that takes us to B and what that enthalpy is, and a reaction that takes us from B to C, we can add these two together, okay? Add these two amounts together, and that'll tell us what it is, in theory, to get from A to C. Okay, so these are additives. All of these things we're going to be working with and using, so don't forget these things. All right, so as I've mentioned, delta H is going to be equal to, or at least roughly, equal to the heat at constant pressure. Okay, so in general, Q and delta H are related to each other. Okay, but there's some important differences. Enthalpy is said to be a state function, and it has different units from Q. So what is a state function? A state function is a function that doesn't depend on the pathway. How did you get there? It doesn't make any difference. You're sitting still, very quietly, right this very second. You have some internal energy. Does it matter? Oops. Come back here. Does it matter how you got there? It makes no difference, right? It doesn't matter if you ate last night or yesterday or if you exercised an hour ago or whatever. You have some state function right this second, and that's an internal energy. It matters not how you did it. You just are there. Likewise, in this room, it doesn't matter if the door opens in 10 seconds. I also have some specific pressure in this room. That's a state function. It doesn't matter whether the door is closed or the door is open. The pressure is what it is right now. Same for volume. The volume in this room is the volume of this room, and it doesn't matter how it got here, it just is. Okay, so enthalpy is similar. Oops, I should just say H. Enthalpy is similar. It's also a state function. And that's how come we can add things together and double them and so forth. It doesn't matter how you got there. It just is the system's amount of heat. Okay. Now, Q is something we measure in the calorimeter experiments. We usually end up with a unit of joule there. Okay. Now, enthalpy is derived, okay, because it's a state function. We can derive it, we can figure it out, we can tell everybody on the other side of the world, and you're expected to tell it in kilojoules per mole. That's the standard scientific language. Now, we're going to be doing a couple of different ways here. We're going to find enthalpy based on our Q experimental data, and we're also going to be able to find H based on values that have been compiled together and are written into tables. Okay, so how you do it depends on the information you have. But we'll work on those later. I also want to mention a few things that you're going to see because enthalpy gets so confusing sometimes. There's so many different enthalpies in the chapter. Now, these are physical. I don't expect you to know these right now. We'll come back to these. These are physical enthalpies. Okay, so this is called, for example, delta H of fusion down here is something that's specific. It is the amount of heat that's released or absorbed when 1 mole of a substance, is going to melt. Likewise, there's one for when it's going to go from a liquid to a gas, okay, at a boiling temperature. I just want you to be aware, to be careful, there's lots of these delta H's. One I didn't get in here, but I wish I would have, is a delta H with this little knot. That's at standard conditions. Okay, that's the enthalpy at standard conditions. What are standard conditions? Standard conditions means that you have a gas at 1 atmosphere. Now, people are trying to change from atmospheres to bars as the official SI unit but most people still think in terms of atmospheres. But your gas is 1 atmosphere or 1 bar. Your solutions, 1 molar, okay? And in the next soon you'll learn, if you haven't learned already, that that is a mole per liter. Okay, that's a standard condition. And it's usually at a specified temperature. Now, the temperature doesn't have to be, but most of them are compiled at 25 degrees Celsius in the tables. Okay, that's not a standard temperature, but it's commonly used. And the last thing about standard conditions is the elements or substances are pure in their standard states. Now, we're going to do this more later, but I just wanted you to note, even though I didn't get this into the PowerPoint, I want you to note that this delta H with the little knot has a specific meaning, and that means at standard conditions. And we'll come back to that. Here's another one, okay? Heat of formation, delta H, heat of formation. These are in tables. Okay, these are commonly brought up in tables. They have, and it's got a specific definition. Again, we're going to come back to that in a few minutes or in a later lesson. But when we're talking about delta H formation, typically standard conditions, okay, this is when 1 mole of a substance is formed. Okay, we're talking about the product. You form 1 mole from the materials in their standard states. Okay, so sodium is standard solid. Chlorine gas is standard as your element. Okay. One more thing. Okay, now I know in Unit 2 we talked about how you had to have whole numbers to write balanced equation. But for thermochemical equations, when you're talking about delta H of formation, the goal is to have 1 mole of your product. 1 mole. So that means if you have to, then you make this a half, or 3 halves, or 5 halves, or 1/3, or whatever it takes to get 1 mole of the product. But we'll talk about that some more. Gosh, I'm almost to the end. Let me make sure I haven't missed anything I wanted to say. I guess I'm okay. All right, so let's talk about energy units for just a minute. Energy, the SI unit is a joule. SI is a unit. And that unit for energy is joules, okay, for the SI units. And I also want you to notice that formula is the mass, okay, kilograms times a meter square over a second squared. Think of other energy things that you know. For example, you know that kinetic energy should be 1/2 the mass times the volume squared. When you look at that in terms of the units, you end up with these units, right? Well, that's the same thing. So notice that your joule is a derived value. It comes from mass and the speed, or the velocity, somehow. All right, and as you should know, a kilojoule is 1,000 joules. Joules are very small, and so we often end up reporting in kilojoules. Now, in the laboratory, okay, which is where we do things in chemistry, we have a unit called a cal, okay, and that's what you measure in the laboratory. And that cal has been defined specifically to be the energy needed to increase 1 gram of water by 1 degree Celsius, and specifically from 14.5 degrees Celsius to 15.5 degrees Celsius. Okay. What matters here is once you've done this work, you can have a standard defined value where 1 cal that we measure in the laboratory is equal to 4.184 joules. Joules being what you report in SI units. Another measurement, and this is one you should all be familiar with, is the capital C cal. Okay, that's your nutritional calorie. All right, that's 1 kilocal with a small c, or 1,000 cals from the defined number that we've given for cals. And then sometimes you'll run across BTUs, and a BTU technically is the energy it takes to raise 1 pound of water by 1 degree Fahrenheit. The conversion factor here is 1,055 joules is equal to 1 BTU. All right, so I thought it might be useful to think about something you might be familiar with all the time. So I looked on the can of tomato soup yesterday, and it said it had a certain number of calories. And then I looked on the internet, it said a different number. So I took the one from the internet just because. And so notice that a can of soup, the whole can, just with water, is allegedly 377 capital C cals. How much is that in terms of the SI unit that you're supposed to report in joules? Okay, so let's just see how that works out. So I have 377 capital C cals. Okay, but what I know here is, it's almost gone here, 1 small c cal in joules. Okay, so I need to convert from a capital C cal to a small c cal. This is a capital cal. Okay, and that gets me into the units from the lab. And then I'll use my conversion factor to tell me that's 4.184 joules in every small c cal. And this works out to be equal to, notice that my units have dropped out and I've gotten from the capital cal to the joule, and this is equal to 1.580 times 10 to the 6th joules. And just to remind you, because it'll come up later in this class, that's times 10 to the 6th kilograms times meters squared per second squared. Now we'll be thinking about that later in gases, but just remember that a joule is a derived unit. It means energy, and it has the same units as any other kind of energy unit. All right, and so I'm out of time, so I just want to say, here's some examples. All right, so I'm going to go through these very quickly. I want to convert my kilojoules to joules. Okay, so in this case, I would take 9 times 10. I guess I'm supposed to take, keeping with my sig figs, 9.0 times 10 to the 6th kilojoules. I want that in joules. There's 1,000 joules in every kilojoule. So this works out to be 9.0 times 10 to the 9th joules. What if this is asking me something about calories? A small letter c. All right, so in this case, this is going to be 9.0 times 10 to the 6th kilojoules. Again, I need to get into joules because my conversion factor is related to the joule. And then I'll have 1 cal divided by 4.184 joules. And this works out to be equal to 2.2 times 10 to the 9th small letter cals. In terms of calories, like nutritional calories, that would be 2.2 times 10 to the 6th. British thermal units, This one's relatively straightforward because I have a direct conversion. 9.1 times 10 to the 6th joules times 1 BTU for every 1,055 joules tells me that there's 8.5 times 10 to the 6 BTUs in that much energy. Okay, so simple conversions, and we'll pick this up soon.